today we'll start talking about the physical layer. In the last class we mentioned that the networking protocols are divided into several layers. There are different classification schemes, but one of them is the 5-layer classification into application, transport, network, data link layer and the physical layer. So we are going to follow a bottom-up approach. We are going to start from the physical layer and move up to the application layer. So what is the physical layer about? Well, it's about communication between two adjacent network nodes. So let's say you have A here who wants to communicate something to B. So how is he going to do that? So he would have to use some sort of a physical signal in order to communicate with B. And the physical layer deals with that. So essentially we decide what signals to send from A to B and how to deal with distortion which might come in between. So let's think about it for a moment. How would we do it? So suppose we were using electrical signals. How would you transmit information? And since we are computer scientists and computers are built essentially to recognize bits, so that's a 1 or a 0. So if we can signal a 1 and we can signal a 0, that should be able to let us send any information across from A to B. So how might we do this? So let's say that you have a wire from here to here, and let's say of course we would need some sort of a reference. So let's say that these are the two wires we send across, and A is going to change the voltage between these two wires and B is going to measure it over here, and by measuring the voltage he might be able to say what was transmitted. So let's say that we say that 1 corresponds to, let's say, plus 5 volts and 0 corresponds to let's say minus 5 volts, right? Let's say we change the polarity. So suppose 1s and 0s are sent out. In theory, in an ideal world, we would see plus 5 volts here, minus 5, right? And we would change the voltage and so on. Right? And let's say there was another 1 and so on, then we would continue at plus 5 volts and so on. Okay, so this seems simple enough, and so it should be easy enough to transmit information, right? Why is it so complicated? And as we see that in wired networks it is not as complicated, but there are some difficulties we will have to address. But in wireless it gets much more complicated. In fact, you have full digital signal processors running on your mobile phones just trying to figure out what was sent, whether it was a 1 or a 0 and so on. Right? Complicated signaling schemes with complicated coding schemes and so on, right, to correct for errors. So let's look at this particular scenario where we just have two wires going from A to B. What could possibly go wrong? And let's think about it. So we have this circuit over here, some sort of a detection circuit. And similarly there could be some sort of a circuit here. So this forms some sort of a loop if you think about it. And what happens if there is a flux, a magnetic flux going through? And so you studied from your physics that the EMF, essentially the voltage that would be induced here is proportional to dB by dt. Okay, so if there's a magnetic field going through this, then a voltage is generated here. And that's going to get added on to what was sent by A. So this is A and this is B. So this signal which is generated here because of some flux going through is going to get added. Okay, so we would have to, if we go back here, we would have to add some signal which might be due to the magnetic flux. So this is one issue to deal with, and you might think, where is this flux coming from? And it may happen that there are lots of people communicating. You could have A, let's say, communicating with B here, but maybe there is somebody else communicating. Let's say that somebody else is communicating over here, and he is varying his signal over here, right? So this loop is itself generating a flux over here. You know that the flux is proportional to the current over here. Right, so this person, let's say C is talking to D over here using their own wire. Okay, maybe I shouldn't call this B, let's call it whatever, B dash or whatever. Right? It's not to confuse with this person B over here. Okay, right, so there is a B double dash here, another flux. So this might actually, some of this might actually go into this loop, right? And in fact, it may happen that A is itself communicating to B using multiple loops. That might happen in practice, right? You have multiple wires, let's say in your Ethernet cable, if you pull it out, you'll see that there are multiple wires in. Each of those would form a loop and they're very close to each other. So the magnetic field generated by one will go into the other loop and will affect the voltage over here. And this is called crosstalk. Crosstalk is just so essentially whatever was transmitted on one wire is affecting the voltage in another wire. Okay, so this is the crosstalk, so to speak. The signal from one wire is going on to the other because of this coupling due to the magnetic field. Okay, so what do we do about this? We need to somehow ensure that this crosstalk is low. So how are we going to do it? So many of you are JE experts, right? And so you probably have figured out the answer. So we need to reduce this loop area. That's one way to do it. And how is it done in practice? Well, there's different ways you would have studied. And one of them is the classic twisted pair. So if you have a landline telephone cable, or in fact pretty much any connector connecting your Wi-Fi router or whatever to some other connector, it will use cables which are twisted. So you will have a wire, let's say I draw this like this, and another wire, so they are twisted together like this in this fashion. Okay, and they are of course tightly twisted together. Okay, I'm just showing it this way to exaggerate it a little bit. So how is this any good? Well, of course you want to keep this loop area small. So let's say we want to tightly twist to keep the loop area small. So that is one advantage. If you keep the area small, then of course there's going to be less induced voltage. But this twisting is also good, that you will have, let's say, a particular flux going through here, and suppose you have the same flux going through here. The wires are twisted, okay, and the net effect could cancel out. Okay, so the twisting changes from this part. You see the black one is above the blue one, and it changes over here. So assuming that all of these are identical, and the magnetic flux is the same in over here and so on, these would tend to cancel each other out, right? So if you twist it tightly and you do this twisting carefully, you do it very well, you can get rid of most of this crosstalk. Okay, so twisted cables were invented in the late 1800s, I think 1880 or so. They were invented, and that was a very good invention because we're using it so many years later, 140 years later. So twisted pair cables are used widely, and they come in different categories. Maybe I should say for twisted pairs. So you have a Cat 3 cable, and this can be used to transmit 100 megabit per second over a particular distance, over 100 meters. So obviously the longer the wire you have, the more attenuation you can expect. We'll talk about that in a moment. So Cat 3, but if you buy a Cat 3 cable somewhere, essentially you can have 100 megabits per second transmission over 100 meters. Right? And Cat 5, as the category number goes up, you have a higher quality. So I beg your pardon, this is not 100, this is 10. Okay. So Cat 5 gives 100 Mbps over 100 meters, and of course you can keep going higher and higher, right? You have a better cable. So here you have 1 Gbps over 100 meters, but if you use a shorter wire, you can go up to 10 Gbps over let's say 50 meters. So these distances correspond to the distance between the two nodes. Suppose you are using a cable between them, this is the distance. Okay, so obviously Cat 6 is going to be more expensive than Cat 3. Okay, so the quality of the material, the quality of the twisting and other things affects the category. Okay. So an Ethernet port, an Ethernet connector if you look into it, you will see that there are many wires coming in, right? And typically you will see 8 wires which correspond to 4 twisted pairs. Right, and so here A is talking to be using this, let's say, so there are 4 twisted pairs going between them, not just one, and they're really close to each other. So the winding has to be pretty good to ensure that the crosstalk between one pair doesn't affect the other pair, or really the crosstalk between pairs is very small. So besides twisted pairs, we also have coaxial cables. So these use explicit insulation, and it might look like this. So you have, let's say, the inner cable like this, and then you have some shielding. So let's say that you have a layer of shielding, some sort of insulation, and outside that, let's say we have say this is another copper wire, right? So this is metal wire, and in between you have some insulation, and then you will also have some outer insulation. Okay, so this sort of a configuration. So here earlier we talked about just two wires. So here, of course, how you're going to communicate using this. So this is really like considered to be one wire, the outer sort of cylindrical metal piece. Yeah, and this inner one is just the other wire, right? So you can think of this as being two wires, right? And so essentially when you communicate, you could have a voltage between these two, right? So this cable is going from these cables are usually thick cables. You might see this sort of a thing if you're getting cable TV at home, right? You'll have a thick coaxial cable coming in to the home, and it will look like this with one wire inside and outer sort of coating around it. Okay, so if you want to communicate, you would put a voltage on these two, and you would change the voltage to communicate the bit information that you're sending across. Okay. So again, this comes in different qualities. So you have thin net coax, and this is supposed to give 100 Mbps over 200 meter distance, and you have thick net coax which gives 100 Mbps over a longer distance, 500 meters. And this, it's called thin because the cable is thinner. It's 0.2 inch diameter, and this one is thicker. So the insulation is much better over here, right? Which is why it's much thicker, which is why you're more immune to noise and interference and so on. So you can get the same data rate at a longer distance. So what else do we use for wired communication? Well, besides twisted pair and coax, you would be familiar with optic fibers. So optic fibers were more rare in the past, but now you have optic fibers even coming to the home. Right? So you may have Reliance Jio or other companies offering, they get an optic fiber to your home and give you a very high data rate. So optic fibers are expensive, but they allow very high data rates in gigabits per second or tens of gigabits per second. Okay, so The reason is that you're using not electrical signals but light rays. You beam them using lasers, and the attenuation is very low. So how does this work? So you have in an optic fiber, you would have this is the inner part of the optic fiber, and you have another material outside. Okay. So this would be called the cladding. So what happens here? You send in a light ray. Let's say you fire it from a laser, and you would want it to bounce off and keep going, right, till the other end of the optic fiber. So there is very little loss over here in these reflections. And when do we have this very low loss? So again, this is something you would have studied for JE and in your 12th standard, when you have total internal reflection. Okay, so you have two materials. So medium 2, medium 1. And the refractive index let's say this is N2 and this is N1, and let's say that you have a signal coming in and it comes in at angle theta. So the question is, what should this angle be so that you get total internal reflection, meaning that the signal completely bounces off. None of the signal actually enters the other medium. And we know that this critical angle is given by sine inverse N2 by N1. So if the angle is larger than this critical angle, the signal would keep bouncing off. If it is less than that, then some of it is going to go into this this particular medium. It's going to escape. So you want your signal to come in at an angle. You want this angle to be large enough so that the whole signal bounces off. Okay. So what might happen in practice is that suppose we look at the situation again over here. You could have a signal, let's say like this, which is bouncing off, and you may have another signal, let's say, which is also coming at an angle of incidence higher than the critical angle. This too may bounce off. Okay, and so both of them reach the other end, and the term used in fiber optics is modes. So we call these modes. And so these different modes are going to come at the other end. And if a fiber allows multiple modes, it's called a multi-mode fiber. So allows multiple modes to pass through. Okay, so essentially you have different, even if it's the same signal, I mean same information going on here. What is the problem with this? Well, the problem is that each of these modes has traveled, each of these rays has traveled a different distance. And so let's say that if the signal, if you were sort of changing the intensity, let's say over here in a particular way, and let's say that the information sent was like this, right? So with this particular mode, it's taking longer to reach, so you might actually see something like this coming through. Okay. So the signal could get delayed at different modes. So when they add up, there is some distortion. So if I add them up at the other end, right? So let's say that let's say this is 0 and this is some intensity. This is this is, let's say when you're transmitting no signal, and here you're transmitting some signal. So essentially we are going to get something which looks like this. Okay. Okay, so you get the idea that these different modes are going to get through and they are going to distort each other in some way. So multi-mode fibers are not the best way to communicate. So it's best to have something called a single mode fiber. So it is designed so that only a single mode passes through. So only one mode passes through. And how could you do that? Well, one thing is you reduce the diameter. But you can also set the you choose materials with the refractive indices to make the critical angle higher. So this depends on N1 and N2. Right, so if you want less distortions with different modes affecting each other, you want less of that, you would want to go for a single mode fiber rather than a multi-mode fiber. Okay. So single mode fibers will obviously be more expensive. So let's talk a little bit about attenuation. So suppose you have a wire over here, and let's say this is the input. So let's say that I am sending a signal with a particular amplitude here, and let's say there is a cable going across, and let's say that at this end you have some amplitude A out, and in any wire there is going to be some, if you look at an electrical wire, there's going to be some amount of resistance, capacitance, inductance and so on, because of which the output amplitude is going to be less than the input amplitude. Okay. So this is just a plain wire, there's no amplifier or anything in between. So what we want to do is we want to measure the attenuation. So how do we measure the attenuation? You might think we want to look at the ratio or something like that, right? And so that's correct. We want to do something like that. It turns out that these could be orders of magnitude different from each other. Especially in a wireless situation, the attenuation is huge. Maybe it's less in a wire. So rather than just looking at the ratio of these, we look at the log of the ratios. Okay, just so that we have something reasonable to deal with, because otherwise the range is just too much. So the log compresses the range of values that we have to deal with. Okay. So the attenuation is measured in decibels. It's given by 10 log to the base 10, the input power by the output power, ratio of the powers, and power is essentially proportional to the square of the amplitude. So this is going to be 10 log to the base 10 A input square by A output square, which is 20 log to the base 10 AN by A out. Okay. And typically people will, when they specify what the attenuation is for a particular cable or wire and so on, they will give it in dB per 1000 feet usually, if you look at charts. So the specifications usually is in dB per 1000 feet. So if you take 1000 feet wire, they will actually send in a particular signal and look at what is the input and output amplitude and power and so on, and calculate this particular quantity, 20 log ratio of amplitudes or 10 log the ratio of powers, right? And they'll give you that number and they'll say this is the attenuation that you will typically face. So what if you have two cables, let's say 1000 feet, and you connect them together? Okay, so what if you have a cable, let's say of 2000 feet? Okay. So I've doubled the length of my wire. Suppose I'm given the specification per 1000 feet. What's the attenuation going to be when I have 2000 feet? So AN is here, A out is my amplitude here, and let's just call this some A dash in between. And let's say that the specification is that you have X dB attenuation, and so you will have X dB here also. Right? So we are told that you put any amplitude here, you will have X dB attenuation when you go over there. Okay, so what does this mean? So this means that 20 log to the base 10 AN by A dash is X, and we are also told that 20 log to the base 10 A dash by A out is X. So what is the attenuation for the entire cable? So the total attenuation is 20 log to the base 10 AN by A out. That's what we want. Okay. So it turns out that is just, you can write it as 20 log to the base 10 AN by A dash times A dash by A out. Which is 20 log to the base 10 AN by A dash plus 20 log to the base 10 A dash by A out. Okay, which is just going to be X plus X which is 2x dB. Okay, so if you add two cables together, you know that each has x dB, the total attenuation is x plus x2x, right? And of course, what if I had x dB here and I got another wire with y dB attenuation here? What is the total attenuation going to be? Well, it's going to be x plus y. Okay? In this particular case, I chose identical cables of the same length, right? But in general, you could have two cables which you are connecting, let's say, of different lengths or different materials and so on. So you would have to add the attenuations in dB units to get the total attenuation. Okay, so by going to the log scale, we've made things a little bit easier for ourselves. Even though we might have very different attenuations in different scenarios, in the log scales the numbers are not that far apart. And if you connect, you have multiple attenuations either due to wireless or wired media, you just have to add them along the end-to-end path and you get the total attenuation. So let's just get a feel of what these numbers are. Let's say if you become a network engineer, right, you need to have this sort of an intuition. So suppose I have, let's say, a wire, and I have, this is my power which was input, and this is the power output. And let's say that I told you that the output power is half of the input power. So half of the power has dissipated on the way, let's say in the resistances and so on, and only half has reached the output. So what is the dB? What is the attenuation in dB? Okay, so attenuation. So remember, in power it is given by 10 log to the base 10 Pn by Pout. So, and if you are taking ratio of amplitudes, you need to make it 20, right? So anyway, this is going to be 10 log 10 to the base 10 2. Okay. So this is roughly, log 2 to the base 10 is roughly 0.303 or something like that, right? So roughly you get 3 dB over here. Okay, so it's not exactly 3 dB, but roughly it's 3 dB. So when you have a 3 dB attenuation somewhere, you know that the power has decreased by half. And you can think what the attenuation would have been, right? But what the amplitude would have been, how much it would have decreased. Right? But 3 dB attenuation means half of your power was lost. So what is the meaning of 6 dB? So suppose the attenuation was 6 dB. How much of the power was lost? Right? So you can think about it, there was 3 dB loss, so power decreased by half, and another 3 dB. Right? So we said when you have wires and you sort of connect them together, the total attenuation is the sum of attenuation in terms of dB. So really we have decreased the power by half when we got 3 dB. We decrease by another half when we get another 3 dB attenuation. Okay. So this corresponds to 4 times, let's say 1 over 4 of, let's just write it in terms of P output. Here it's going to be 1 over 4 of the input power. It's 3 dB followed by another 3 dB. Okay. Right, and you might want to know what is 9 dB? Well, you have another 3 dB drop, right, in the power. So that would be 1 over 8. What about 10 dB? So what does this mean? So that means 10 log to the base 10 Pn by P out is equal to 10. Right? So this is the attenuation, and so we get this. So what does this mean? So Pn is equal to 10 times P out. So if somebody tells you I have a 10 dB drop in signal power, or let's say I have attenuation of 10 dB, that tells you that the power is dropping by a factor of 10. Okay, so 3 dB corresponds to a factor of 2. This is, I'm talking about the power, and this is the dB in attenuation. 6 dB is 4, 9 dB is 8. So these are all approximations. So it's approximations, and 10 dB corresponds to a factor of 10 drop in power. So network engineers also use dB scale to look at power. So we've looked at dB for attenuation, and we said that you take 10 log of the ratio of powers to the base 10. That gives you attenuation in dB. But dB scale, actually to be more precise, dBm and dBw are scales used for power, absolute power. So attenuation is only a relative number, so you take the ratio of powers. Right? So why do we do this? Well, again, because powers come in a very wide range of values. Right? You could have milliwatts, you could have watts, you could have nanowatts. Right? So writing the absolute numbers could be quite tricky. So if you put it in the log scale, it helps a lot. So what is dBm? And in fact, if you're making measurements with an app, let's say of wireless signals, you might see units of dBm. So how do we define dBm? So let's say that the power, this could be the power that we are transmitting somewhere, right, over a wire or over a wireless channel. So let's say that the power is given by is P, and we don't want to write it in absolute units, which is going to be, I mean, the range of values is too much. So what we do is we take 10 log to the base 10 of that power, and we compare it to 1 milliwatt. So this is a reference. So we compare it to 1 milliwatt, and we take 10 log 10 to the base of that ratio, base 10, and we take the ratio. And this gives us the power in units of dBm. So let's take a few examples so that we get familiar with this. So let's say that we look at, let's say that P is 1 milliwatt. So if we write this P in terms of dBm units, it's 10 log to the base 10, 1 milliwatt by 1 milliwatt. Okay, so this cancels, and we end up with 0. So log 1 is 0. So 0 dBm. Okay. So somebody tells you that I have power of 0 dBm, you know that he means he has 1 milliwatt. Okay, suppose he says, as I am receiving 0 dBm, he's receiving 1 milliwatt. What if I have power of 10 milliwatt? So it's 10 log to the base 10, 10. So I get 10 dBm. What if I have a power of 1 watt? Ten log to the base 10. So that's 1000 milliwatts. by 1. Okay, so this is going to be 30 dBm. 1 watt is 30 dBm. And of course 100 is going to be 20 dBm, right? And just let's take a few more examples. What if I have 2 milliwatt? So just like we had seen in the earlier case for attenuation, so you have 2 over here, and this is 0.303, right? So this is roughly 3 dBm. So what if I have a microwatt, 10 to the power of minus 3 milliwatt, so that's a microwatt. What's it going to be? Well, 10 log to the base 10, I have 10 to the power of minus 3 here. Okay, so this is going to be equal to minus 30 dBm. And in fact, when you're making radio measurements in 4G and 5G, you'll see something as low as minus 80 dBm or minus 100 dBm. Okay, very, very small power. So you can imagine how little power your phone is receiving. It's in not microwatts, it's in nanowatts or something of that scale, right? Or even less than that. So when you have such low amounts of power coming in, you can imagine how difficult it is to figure out what the signal is. Okay, which is why you need a lot of signal processing in your phones. Okay. Let's look at some typical charts for attenuation for wires and fibers. So plotted over here on the y-axis is the dB in attenuation per 1000 feet, and on the x-axis I am showing the frequency. So as you can see that at 1 megahertz, let's say the Cat3 cable has, let's say, only a 10 dB attenuation, right? And it goes up with frequency. And Cat5 is clearly better, the attenuation is less. And coaxial thicknet is even better than Cat5, right? So of course prices also are going to vary, so you would have to depend, given your budget, which one you want to use. Right? And depending on the performance you want and the length of the wire and so on. Okay. So you might wonder, why does it change with frequency? Why should it have anything to do with the frequency, right? And so just basics. So you have if you want to model your wire, you'll have to write what the resistance is, and you're going to have things like capacitances kicking in. Okay. And also inductances. Okay, so these are the symbols we use. You would have used it for your JE and so on. Right? So this is the capacitance. So we would want to model our wire in terms of resistances, inductances, and capacitances. Right? And you would know from your physics that resistance, of course, doesn't depend. I mean, it doesn't have anything to do with the frequency of the signal, but the inductances and capacitances do. Right? So that gives you some intuition that if you have a higher frequency, you might see more attenuation. Right? So just think of a simple circuit which looks like this: a resistance and a capacitor, right? Something like this. Let's say that this is your input and this is your output. And you can look at what the output is going to be based on the input when you change the frequency, right? So suppose you have a frequency of f0 here, what is the output going to be? And you can show that this is a simple example of something called a low pass filter, okay, which means that if your frequency is low, it gets through pretty much without attenuation to the output. But if you have very high frequency, this capacitor is going to dampen out things. It's not going to let that frequency through, right? So if you have a very high frequency like this, at the output you're going to see something of a lower amplitude, right? You might see something like that, right? Depending on what this capacitance and resistance, right? So that's just to give you an intuition about why these change, right? You don't need to know the full mathematics behind. So what about optic fiber? So this is what a typical attenuation chart of an optic fiber would look like. And here we are looking at very different range of frequencies. Here I plotted 1 megahertz, 2, 4 megahertz and so on. Here you are looking at light frequencies. Okay, you are transmitting light rays through which have very high frequencies of the order of 10 to the power of 14. So if you look at the wavelengths, it's of the order of hundreds of nanometers, okay, 1600 nanometers, 800 nanometers and so on. Right, so these are the wavelengths corresponding to these. And just look at the attenuation here for 1000 feet in terms of dB. It's between 0.2 and 2. Okay, so compare the numbers here and here. So here you have an order of magnitude higher attenuation on the dB scale compared to here. So attenuation is very, very little in optic fibers. Okay, so that's the reason why you can get a lot of very high data rates using fibers when compared to things like twisted pair or coax. Okay. Also, another reason you get higher data rates is because of the total frequency range you can use in the optic fiber. Okay. So here you can think about after a certain frequency range, as you go up, the attenuation becomes too much. So you can't really use the cable at all at very high frequencies. Okay. And essentially the more the frequency range you can use to transmit, the higher the data rate that you can push through. Okay, that's the intuition. And so since here you can have a lot more frequency ranges that you can use to transmit information, you can push through much more data. Right, so optic fibers can give you terabits per second, I mean in theory, right? We don't use those kind of bit rates today, but in theory you can have, it's sort of almost limitless. Okay, so but of course optic fibers are much more expensive. So let's talk a little bit about wireless links. Okay, so here let's say you have A and B. Now A is going to transmit using an antenna. Right, so there is he has some, let's say, radio, and out from it comes an antenna. The antenna might be hidden in things like mobile phones, right? But it's there. So the antenna is going to radiate signals and it's going to be received by B. Okay, so there is some power being sent out over here. Okay, and this may be of the order of milliwatts being sent over it. So again, the standardization comes into the picture here. So the Wi-Fi standards will say that you are not allowed to transmit more than a certain power. Okay, just because the more power you send out, the more interference you cause to other radio signals, right? Even if they don't use your frequency, there could be some spillover into other bands. And also people are worried about health concerns and so on, right? There hasn't been any negative effect shown, at least at these power levels, but people are worried, if you have so much of radiation, is it going to cause any health problems? So for all those reasons, you have a restriction on how much power can be actually transmitted from a radio. So how much of this is going to be received over here? So let's say that P out is the power that is being received over here. Okay. And a simple model is going to be like this. So you can think of this, suppose this entire power gets spread over a, let's say we think about a sphere, and let's say that this is the distance is d. So you have a sphere over here, and the area is 4 pi d square, and let's say that the antenna area is A. So what is the power that I receive over here? So this antenna is roughly occupying some space over here in this sphere, and if this power is uniformly distributed over that sphere, so P out is going to be proportional, of course, to P in, and the area. The more the area of the antenna, the better. But this input power is spread out over some surface, so it comes out something like that. Okay? So this is the intuition why your power decays a lot in a wireless system. Okay? Because as this D gets larger, you get very little power at the other end. And in fact, people have shown in practice it's not such a simple decay. Due to other reasons, you may have maybe the power decay, the power received is actually proportional not to 1 over d square, but some 1 over d to the power of alpha, where alpha is between 5 and 2. Okay, that's more realistic. And some of those reasons we'll see in a moment. Okay, why you would have more decay than this. Okay. But to improve performance, sometimes wireless engineers will use directional antennas. So suppose you have these are not mobile users. Suppose they are fixed. Then you can actually have one antenna pointing to the other antenna, and you might have directional antennas. So you might see, let's say, some sort of a dish antenna like this. Right? So suppose it might look something like this. Right? It's a circular dish, and it points in a particular direction. And you can also have a receiver which looks something like that. Right? Okay. So all the power is focused in a particular beam. So you can actually plot the direction. So most of the power goes as a lobe in this direction, very little in that direction. Okay, so you get better received signals in this sort of situation using directional antenna. Okay. So of course, now things are much more advanced, and those of you who might want to do communication courses in electrical engineering will learn about multiple antenna, multiple output systems. Okay, so you can have multiple antennas, let's say 4 antennas at your transmitter, and you can have multiple antennas at the receiver, right? And this, by using these cleverly, you can actually build in some amount of directionality and so on, right? And you can get better signals received at this end. Okay, so there are other advantages to MIMO too, besides just having directional signals. Okay, and now the latest thing is something called massive MIMO. So if you hear about these people developing 5G and the future 6G technology and so on, so they will have not just 2 or 4 antennas at the base station. They may have hundreds of antennas, right? And of course, to build such systems and do the signal processing is very, very tricky. Okay, so what can go wrong in a wireless situation? So first of all, you can have interference. Okay, so here you have, let's say, A is sending to B a signal, and as it is, it gets attenuated because the signal spreads in all 3 dimensions. But you could have somebody else, C transmitting to D, let's say, and some of this signal also reaches here. Okay, and of course, A's signal might also reach here. Okay. So these signals get added up, and this is called interference. It's just like we saw crosstalk for the wired situation. Then you might have obstructions. So in the wired situation, we said with twisting and so on, you can reduce the crosstalk, okay, reduce it a lot. Whereas here, your antenna is just open, right? It can receive any signal sent by anybody else. So you may have a situation like this: A is sending it to B, and there is an obstruction in between. This could be a building or whatever, or a car or a wall or something like that. Yeah, and so what is the, I mean, how is this going to affect the signal? Well, clearly the signal that's going here might be completely absorbed by the building. But sometimes it may happen that you actually are able to communicate even when there is some obstacle in between. Okay? So luckily for us, some of the signal can go around. So diffraction helps us. Okay, so some of the signal might actually go around and we get part of the signal. Okay? But if you're, let's say, in direct line of sight of this particular antenna, if you're B and you're in direct line of sight, so that is the term people use, line of sight, which means that there is no obstacle in between. You can actually see the antenna if you're looking from here. Then you'll have good reception, but if you suddenly go behind a building, then the reception might decrease. Okay, the signal quality might decrease, okay, and your receive power in terms of dBm may drop. So there are other issues also, something called multipath. So I have an antenna here, A's antenna is like this, B's antenna is here. And this is the direct signal coming from A to B. But it's possible that there are also reflections. So suppose there is a car nearby, the signal might actually bounce off. Let's say there is another object over here. Some of the signal may bounce off and come over here. So this path is longer than the direct path. Okay, so suppose there is a signal which is being sent over here. Let's say that this signal is something like this. So let me draw it this way. Let's say that this is the signal which was directly sent. Now this signal coming over here is a little bit delayed, and because of the reflection it might actually get flipped over. So what you might see is something like this. You can similarly, let's say this one, there may be some, the reflection might cause something like this coming through, right? So maybe it is like this. Okay, so the amplitudes will be different. The delays will be different, but also there could be a phase change, which I'm just showing crudely in this fashion, right? And all these get added up at the receiver, so he might see something very different from what was transmitted, something like this, maybe the total signal received. So the actual situation will depend on how many obstacles are there. So this is called multipath. So it's analogous to our multi-mode that we had in fibers. But the problem with wireless is that you don't know how many multipaths you're going to have in advance, right? So maybe a car suddenly comes and parks, or the trees move or something like that, and all these multipath effects keep changing over time, right? So In real time, your radios at both ends are going to try to figure out what these multipaths are, and they're going to try to adjust to those. Okay, so communications is a very advanced theory. If you'll have several courses in electrical engineering which you can study for this. Okay? So multipath causes distortion over here. It delays signals. You have different path signals going through various paths and getting added up at the receiver. Okay, so this is a little bit of an initial lecture for physical layer. In the next class, we'll talk about actually how to transmit signals. So till now I've introduced, I just said when you have a bit 1 and you have a bit 0, I might send a pulse like this, or I might send a pulse like this, right? So that's sort of the simplest signal, but we may have to do something more based on the practical constraints that we face. So the term for that is modulation, and so we'll talk about how exactly to modulate signals to transmit bit information across a wired or a wireless link.